In this video, we will do an application of vector functions to projectile motion. So the example I want to look at is an object is launched at a 60-degree angle relative to the horizontal at 49 meters per second. And in part A, I want to ask the question, how far away does the object land? So questions like this are really common problem in physics. So specifically when you talk about mechanics in physics, answering questions like this. So if you've taken physics before, you may have already answered problems like this, and typically you do that by breaking things down into like the x direction movement and the y direction movement. We're going to do so sort of holistically, consider both of those together using vector functions. So how far away does the object land? So let's begin by drawing a picture of the situation. So let's first draw a picture. So I'll draw a picture. Okay, so in the picture, let's say that we have some ground here, and then we have this object. So I'm going to indicate the object with a dot, and the object is launched at a 60-degree angle relative to the horizontal. So let's say that this is making a 60-degree angle, so that means it's got to be like sort of launched up at this direction. So this is a 60-degree angle right here. So when the object is launched, it's initially going to be launched at that direction, but then gravity is going to kick in. It's going to start to curve it down, curve it down, curve it down. It makes a sort of parabolic path, and eventually somewhere down the road it's going to land. Okay, so this right here is the landing spot. The landing spot, we're not sure how far away that is from the launch spot. So this is the launch, whoops, sorry, not launch spot. All right, so having a picture is definitely going to be helpful. We want to draw a picture. Other things that we're going to want to do are define axes. So we are going to want to put the origin somewhere and then indicate an x-axis and a y-axis, because this is a two-dimensional problem based off of the picture that we are drawing here. Okay, so it's typically nice to place the origin at a spot we have information about. So in this case, we know specific information about the launch spot. We know the angle that the object is launched at. We know the velocity that the object is launched at. So I'm going to put the origin at this launch spot. And that'll depend on the problem, what the best choice is for the origin. Sometimes there's more than one choice for the origin that works. And I'm just going to make the horizontal direction be my x-axis. So this is going to be my x-axis. And then I'm going to have a vertical direction, and I'm going to have that be the positive y direction. All right. So another thing that it's good to do at the start of these problems is to also define any variables. So we already have an x and a y sort of indicated in terms of our axes. Another variable that would be good to have in this problem is t. So let's let t be the number of seconds, that's the unit of time in this problem, seconds after launch. So number of seconds after launch. All right, so we have a picture, we've defined some axes, some variables, in this case t, an x and a y. All right, so now let's write down what it is that we're given and what it is that we want to find. Okay, so what we want to find is sort of the final position. We want to know what the position of this object is at that landing spot, because if we know that position, we can figure out how far away it landed from the launch spot. So we need to know the final position. What is that we're given? So one thing that we're given is the acceleration due to gravity. So even if a problem like this doesn't tell us what that is specifically, the acceleration due to gravity is something that's known. So that is 9.8 meters per second squared. That's the acceleration due to gravity. And gravity is accelerating stuff downwards, towards the ground. So downwards, technically towards the center of the Earth. So downwards. So that's something that's given, or maybe I'll put given slash things that we know. All right, what are some other things that are either given or that we know here? Well, so we know this acceleration due to gravity. I can also write this using my vector notation. We would write a vector of t equals, if it's just pointing downwards, that means it has no I component. So it's 0 I hat. But the j component is negative 9.8. So we can write this vector function for the acceleration, and that'll be useful to have. Okay, so another thing that we know is that the speed, which is the magnitude of velocity, initially, so when t equals 0, okay, that is given to be 49. Okay, so taking the magnitude of v of 0, this tells us the initial speed. Okay, so can I use that initial speed and this angle that it's launched at to figure out what the velocity, that initial velocity vector would be? So let's talk about how we would do that. Okay, so if I think about this as the launch spot, so my initial velocity vector is pointing upwards like this. So I have a velocity vector, it's pointing upwards like this, because that's the angle that this object was launched at. So now if I draw a horizontal line, and then a vertical line, to make a right triangle like this, we know that this angle is 60 degrees. And if that's 60 and it's a right triangle, that means the other angle is 30 degrees. Okay, so if we remember our 30, 60, 90 stuff from geometry, so if I have a 30, 60, 90 triangle, and the side opposite 30 is 1, then the side opposite 60 is root 3, and the hypotenuse is 2. So in my picture, in the actual velocity, initial velocity vector we have, this hypotenuse length is 49. That's what's given to us. So these two triangles are similar. They are similar triangles. Similar triangles. In fact, the ratio, the common ratio between these is, to get this hypotenuse to become that hypotenuse, we have to multiply by 49 over 2. So I do the same thing to each of the legs to get the legs of this larger triangle. So the vertical leg is going to be 49 root 3 over 2. And the horizontal leg is going to be 49 over 2. All right. So using this, I could write down this initial velocity vector in terms of its I and j components. So its I component is 49 over 2. And the j component is 49 root 3 over 2. And that's the j component. Both of these numbers are positive because based off of the direction this vector is pointing in, its x component is positive, and the y component is also positive. All right, so that is something that we know. There's one other thing that's sort of known or given, and that's we actually know something about a certain position. We know something about the initial position, r of 0. The initial position, because we said the origin is where the launch spot is, the initial position is just 0. 0 I hat plus 0 j hat. Okay, so that might seem kind of trivial, but it is important. We are going to use this. This is our initial position. Okay, so far we've just spent a lot of time kind of setting this up, but this is important. The more we practice these problems, the more quickly some of this stuff will go, like writing down the acceleration due to gravity, and these things like writing down the initial velocity vector, position vector. All right, so now that we have this, we are ready to solve this. So my starting point is going to be to use my acceleration function. So a of t is equal to negative 9.8 j hat. So we have this acceleration function. And because my ultimate goal is to find the final position, so we are trying to find the final position, we are going to need to get r of something. We need to get the position function. So that means we're going to need to take some antiderivatives if I'm going to want to get from acceleration to position. If I take the antiderivative on the left-hand side, we get velocity. Taking the antiderivative of a vector function is kind of like taking the derivative of one. You take the antiderivative sort of component by component. So in this case, there's just a j component here, and that antiderivative would be negative 9.8t, and we'd still have j hat. And just like we're used to when we take antiderivatives from calculus, there's a plus c term. There's also going to be a plus c term, but in this case, I'm going to call it c1 actually, and this is going to be a vector because we're talking about vector functions. So c1 is a constant vector, not just a number now. So it's a constant vector. This is like having a plus c, although in this case we have plus a constant vector. All right, so next we can solve for that constant vector by plugging in t equals 0, because when t equals 0, we know what v of 0 is. We know that initial velocity. So if we do this, if we plug in, we get v of 0 equals, on the other side, we will get 0 j hat when we plug into that first term, plus that constant vector c1. Okay, but we know what v naught is. If we write down what v naught is, we can get c1. So c1 is equal to v of 0. It's 49 over 2 I hat plus 49 root 3 over 2 j hat. So that's c1. All right, so now we can plug this in to our velocity function. So our velocity function v of t is equal to, if I plug c1 in here, we are going to end up getting 49 over 2 I hat. And then for the j hat term, we are going to get plus 49 root 3 over 2 minus that 9.8t j hat. So I'm combining some of the like terms, both of these ones that have a j hat, and I'm factoring the j hat out. All right, so we got a velocity function now. Well, we need to get a position, so let's antiderivative one more time. So let's do another antiderivative. Now we'll get position function. So we take this antiderivative component by component first. So for 49 over 2, we'll get 49 over 2t I hat. And then for the next term, so with the j hat, antiderivative of the 49 root 3 over 2 is 49 root 3 over 2t. And then for the next term, we would end up getting, the power becomes 2, we'd get t squared, but we have to divide by 2. And dividing 9.8 by 2, we get 4.9. So we'll have minus 4.9 t squared j hat. And then because we took an antiderivative of this vector function, we have a plus a constant vector, which I'll call c2. And that's the reason why I called the first one c1. It's because I knew that I was going to get a second one. And that's why I labeled one of these c1 and the other one c2. All right. So just as before, now let's solve for the vector c2 by plugging in t equals 0, because we have information about what's going on at t equals 0. So if I plug in t equals 0, on the left-hand side, we get r of 0. On the right-hand side, the first part becomes just 0. So we get 0 I hat plus 0 j hat. And then we have plus that vector c2. But we know what r of 0 is. R of 0 is given to us up here. It's just 0. So overall, what we get is that c2 is just 0. Or we could write 0 I hat plus 0 j hat if we wanted to. So this is 0 I hat plus 0 j hat, but that's just the 0 vector. All right. So now we know what r of 0 is. We are ready to plug that in to our position function. So now I can take what c2 is and plug it in here for the C2. And that'll give us that r of t equals 49 over 2t plus 49 root 3 over 2t, and then minus 4.9 t squared j hat. All right, so we have this. All right, so I just scooted everything down to give myself a little bit more room. Now we have a function for r of t. So this right here is our position vector function. And the thing that's in front of, ooh, whoops, I think I forgot to write I hat on this. Yeah, so I forgot to write the I hat after the t. So we have 49 over 2t I hat. So that whole thing is my position vector function. And the 49 over 2t is the x component of the position vector at time t. And the thing in the parentheses here is the y component at time t. Oh, there's one thing that looks weird there with the power. Let me fix that. Okay, so this power should have been inside the parentheses. 4.9t squared in the parentheses. And this whole thing was the position vector function at time t. So we want to know when the object lands. We want to know something about when the object lands. So the object lands when the y coordinate, or the y component, is 0. So let's set that y component equal to 0. So we are going to get 49 root 3 over 2t minus 4.9 t squared. That's the y component, and we want to set that equal to 0. Okay, let's rewrite 4.9 as a fraction. This is 49 over 10. So I can see some stuff common that I can factor out here. So we could factor out a 49, we could factor out a t, and I'm also going to factor out a 10. And when we do this, what we'll be left with from the first term is a 5 root 3. And then from the next term, we'll be left with a t, minus t. And this whole thing equals 0. All right, so now that I have it factored, I can set each part equal to 0. So from this first fractional thing, we get t equals 0. And from inside the parentheses, we get t could be 5 root 3. All right, and the units for time here were seconds. All right, so we're getting two values for when y equals 0. And that's because 0 was the launch time. So one of these times is when we launch it. That does correspond to when y equals 0 as well. And the other time is 5 root 3. This is going to be the landing time. All right, so here was our position function. Let's now plug in 5 root 3 into this. This is the landing time. So doing that, we end up with 49 over 2 times 5 root 3 I hat for the first part. And the second part needs to be 0 j hat, because 5 root 3 was supposed to make the y component 0. That's how we found the 5 root 3, by setting the y component equal to 0. All right, and if we simplify this x component, if we multiply it out a bit, this gives us 245 root 3 over 2. All right, so drawing a picture of this, so let's say that this is our ground, and here is our object. And the object is being launched at an angle of 60 degrees relative to the horizontal. And when we do that, it makes this, fires at the angle, but then it makes this parabolic path, and then it lands somewhere. Okay, so let me extend the ground, and then it lands somewhere. So the time when it reaches this point, this landing point, is 5 root 3 seconds. It takes 5 root 3 seconds for this object to land. And what this 245 root 3 over 2 represents is, it represents 245 root 3 over 2. It represents the x component of this point relative to the origin. So that is this horizontal distance away from the origin. So the answer to our question about how far away it lands is, it lands 245 root 3 over 2. And what were the units? In this problem, they were meters. This many meters away. All right. So there's a lot to this problem, a lot of steps. So I definitely encourage you to pause the video, rewatch it, and if you have questions about it, definitely ask. Alrighty, so let's do another part of this problem. So let's find the slope of the path made by this object at t equals 1. So this is a bit of a review problem from section 11.2. We want to use our parametrization. So the path is a parabola, and the path is parametrized by, so the x component of position was 49 over 2t. And the y component of position was 49 root 3 over 2t minus 4.9 t squared. So we are just taking the x component of this position vector and the y component, or the j component of this position vector, and making those what x and y equal in our parametrization. Okay, so now that we have it parameterized, we can use our formula for the derivative. So we'll recall that dy dx is equal to dy dt over dx dt. And when we take those derivatives, so dy dt will end up being 49 root 3 over 2, and then minus, bring that 2 down, we'll get minus 9.8, and then t. On the denominator, the derivative of derivative of x is just 49 over 2. All right, so we want to know what dy dx is at t equals 1. And if we plug 1 into this, I've gone ahead and done this and used a calculator to work out what it is. It is about 1.33 if I round it to 2 decimal places. So that's the slope. That is the slope of this tangent line. All right, so I want to do one more part of this example. So this is another review problem. Let's find the total distance the object traveled. And to do this, we're going to need to set up an integral. So we will use a calculator or a computer to evaluate the integral. So as a reminder, the total distance that an object travels is, this is another way to say the arc length. And the formula for arc length is it's an integral from a to b. And you take the magnitude of velocity, because what that equals is an integral from a to b. And the magnitude of velocity is going to be square root of dx dt squared plus dy dt squared. And we stop there because we don't have a z component in this problem. We just had an x equation for our parametrization and an equation for y, but we didn't have a z equation. So that's why we stopped there. If we did have a z equation as well, you'd also have a plus dz dt squared inside of the square root. Okay, and then I have to put this dt at the end for proper notation. All right, so we are going to get an integral from whatever our start time was to the end time. So the start time is 0, and the end time is 5 root 3. So 0, this was the start time for our path. It was when it was launched in this problem. And the end time is when the object landed, because that's what we cared about. Okay, and then we're going to have the square root of dx dt squared. So dx dt was 49 over 2. We just worked that out. Square it. Plus dy dt squared. And dy dt is 49 root 3 over 2 minus 9.8t. And we have to square that, dt. And when we work out what this is with a calculator or a computer, because that's what I wanted us to do in this problem, just set up the integral. But now at this point, we can use a calculator or computer to evaluate what this is. This is 292.84 meters. Okay, so that is the total length of this parabolic arch. All right, so in terms of our goals for this section, we have now done an example involving projectile motion using these vector functions.